point of view, right? So whenever we are talking about a switch, and it is a voltage withstanding capacity. Suppose the voltage withstanding capacity, this switch can be unipolar switch or a bipolar switch. When it's a current carrying capacity is there, it is either a unidirectional switch or a bidirectional switch. What is the difference between a unipolar, bipolar, and unidirectional and bidirectional? Whenever we are talking about voltage, this is either positive voltage or a negative voltage. So unipolar means only positive voltages. The switch can be applied only positive voltages. Whereas if you are talking bipolar, the switch can be applied both positive as well as negative voltage. Whenever you are talking about current, current is a current flows in different directions. So you can say that the current is in a unidirectional current or a bidirectional current, right? And whenever you are talking about control aspect of this switch, there are three kind of control aspects. So that is uncontrolled, semi-controlled, and full controlled. Right. Uncontrolled means you don't have any control over the switching on and switching off of the switch. Semi-controlled means you have some form of control over the switch on and switch off characteristics of the switch. And full control means you have the complete control over the switching on and switching off of the switch. Now, whenever you are talking about a switch, you might have known different kind of switches like which is identified by pole and through SPST, TPST, DPDT, and SPDT. Right? Sorry, it's wrongly typed. SPST, DPST, DPDT, and SPDT. Right. What is SPST? Single pole, single throw. Single pole, single throw. Single pole, double throw, double pole, single throw, and double pole, double throw. All right. There are basic. If you talk about pole and through of the circuit, this of the switch can be of four different types. Right. Why switch is important? Because anywhere, whenever we are talking about a power electronic device or any kind of device, switch is very essential because without switching, you don't have any kind of uh, rectification or any kind of control over a device, right? So whenever we are coming about a rectifier, all of you know what is rectifier. Rectifier is nothing but a device which converts a AC signal to a DC signal, right? So how the rectifier is classified? Rectifier is classified in many ways. One is uncontrolled rectifier. Uncontrolled rectifier, as I have told before, controlling capacity. Uncontrolled rectifier is only diodes. Because in a diode, you cannot control the forward, the time. You cannot control whether the diode is in forward bias or a reverse bias. Whenever the current is flowing to a cathode to anode and anode to cathode, you cannot control it. So that's why it is called a uncontrolled device. So rectifiers made up of diode are called uncontrolled rectifier. Similarly, there is a full control. Full control means SCR, silicon control rectifier. SCR is silicon control rectifier where this is a type of switch where you provide a external gate pulse to control the switching on and switching off of the switch. So that is called a fully controlled switch, SCR, silicon control rectifier. Whether in this kind of switch, you provide an external excitation, pulse excitation to the switch so that the switch can be turned on or turned off according to your wish, right? And there is semi-control. Semi-control, as the name indicates, it is the intermediate portion of uncontrolled and full control that it comprises of diode as well as the SCR. Now, whenever we are talking about a uncontrolled diode rectifier, we have a single phase and we have a three phase. And whenever we are having a single phase, that is again classified into half wave as well as full wave. You might have studied in your basic electronics course what is a half wave rectifier, what is a full wave rectifier, what is a in the full wave also there are two types, what is a center tap and what is a bridge, right? Similarly, in three phase, again you have a half wave and full wave, but here there is in full wave there is no center tap configuration. In full wave, it is directly bridge configuration, right? Same kind of classification to all the uncontrolled and full control and semi-controlled classification. You have two different types, whether the source is a single phase or whether the source is a three phase. In both single phase as well as three phase, you have either have a half wave configuration or have a full wave configuration. All of you know what is the difference between a half wave configuration and full wave configuration, and which one is better, which one is not better, right? So let's take this particular circuit, very simple circuit. There is a switch, there is a diode, and there is a supply, AC supply, and we have connected a R load only. We have connected a R load only. So everyone can do this in Simulink with or without the switches. For the timing, leave apart the switches. We don't want the switch. Just a yesterday we saw how we can do it. Just a source, a diode, and a load. Now, whenever you are doing this, what will be the actual waveform over here? See in the right hand side. This is initially the source voltage, and here you have the, because it's a half wave rectification, the negative half cycle is missing. So this is 0 to pi. So only positive half cycle. This is V0 and this is the Vm. And what about the I0? I0 is nothing but V0 divided by R. So V0 divided by R is the I0. So source voltage, load voltage, as well as load current. We are assuming this switch is closed, right? We are assuming the switch is closed. Now, after doing all this, we need to find the average voltage across the load. Average voltage across the load. Obviously, it is the output voltage. So V0, we know the formula for average 0 to 2 pi Bm sin theta d theta, because the source wave is a sinusoidal wave. Assuming the sinusoidal wave, V0 equal to integration of 0 to 2 pi Bm sin theta d theta divided by 0 to 2 pi d theta. So it will be the average output voltage is Vm by pi. Whenever it is Vm by pi, you can always write it is at root 2 Vrms by pi. Vm can be represented as root 2 into Vrms. And then what is the RMS voltage across the load? Vrms equal to root underscore 1 by 2 pi integration of 0 to pi b square d theta. That is Vm by 2. That is Vm by 2. Similarly, average load current, because it's a purely resistive load, no need of more complicated equation. I0 equal to V0 by R, as simple as that. So I0 equal to Vm by pi divided by R, so Vm by pi R. So you can find out the DC power, you can find out the AC power, as well as you can find out the efficiency. As you can see, the half wave rectification efficiency is pretty low. This is around 40%. This is around 40%, right? So it is not advisable to use a half wave rectifier. It is not advisable to use a half wave rectifier because of low efficiency, 40% only. Suppose you are giving a 100 volt AC, you will only get a 40 volt DC, which is not good enough, right? So form factor, ripple factor, everybody knows what a form factor, everybody knows what a ripple factor. Ripple factor is 1.21. This also pretty high. That means indicates that 121% of the AC component is present in the output DC, which is very, very high. It is more than 100%. All of you know what a ripple? Ripple is nothing but undesired components, right? And low undesired components in the output voltage that should not be there, right? So this is the basic theoretical aspect of a rectifier with R load. Similarly, you can go for rectifier with L load. It will be somewhat more complicated. Let's first do the rectifier with R load in Simulink. Everybody understood the theory part, so that we can move on to the practice part. It's pretty easy to do this because I am showing both, because you should understand both the theoretical part as well as the practical part. So have something open. Let's create a new file. Close it down. Simulink library browser. Simscape. Go to Simscape. Power system. Specialized technology. Fundamental blocks. First work is Power GUI. First work is Power GUI. Then go to the sources. Right. Then go to the power electronics. Here directly you can find a diode. As simple as that. Then go to elements. Here we need to find a series RLC branch. Polar. Let's suppose only are loaded to 100 ohms. Right. Now we need measurement. Go to measurement. Voltage measurement. Okay. This is one measurement. We need both input and output measurement. Here we are doing it. Then go to current measurement. Source current and load current. Then we'll go for scope. This scope, number of input ports, so we'll change it out. Here. Directly we can do it. Voltage, current, voltage, current. Let's run it. Taking some time. Okay, it's working. Then we see the outcome over here. As you can see, this is the initial voltage, source voltage, source current, load voltage, as well as load current. Right. Similarly, you can find out the diode voltage as well as diode current. How to do it? Go to signal routing, bus selector, just the bus selector over here, double click, signal 1 and signal 2, double click on the bus selector, remove this thing, diode current, diode voltage. Okay, let's run it. Here you can see the diode current as well as the diode voltage, and here you can see very well see the source voltage, source current, load voltage, and load current. Any doubt regarding this? Any doubt regarding this? Here we are getting a simple half-wave rectifier with R load. The theory I have shown, and this is all the graphs. And next we will go for the L load, calculation of rectifier with L load. And then also we can do it. But straight away I am showing a L load how to do it. Just change it to a L. $15 millihenry. Okay. 213 to over here the source voltage, source current, load voltage, load current. As you can see, the load voltage and load current are same, and here you can see a glitch over here. If you increase the value of inductance, let's suppose 35 Henry, then the glitch will be much more permanent, much more. That millihenry. Check it out. No, it's reducing. Millihenry. This glitch you can see over here in the output voltage, right? This is a simple rectifier with L load. This is a simple rectifier with L load. Now let's see the theoretical background of it. Here you can see the L load, the circuit and the waveforms, relevant waveform. Vs equal to V0 equal to, if you apply Kirchhoff's voltage law, you will get Vs equal to V0 equal to L di0 by dt. That's equal to Vm sin omega t. And I0 will be Vm by omega L 1 minus cos omega t. So V0 will be Vm sin omega t. So here the input equal to the output. Input voltage is equal to the output voltage, right? That's here what you can see over here. Input voltage is equal to the output voltage, but here there is a slight glitch with respect to the inductance value. Clear? So again, similarly, you can go for the C load as well. C load, RL load, everything you can do. This is directly from PS Pimra Power Electronics, and I'm doing it over here. For C load, directly I cannot connect C, so I have to connect a RC. I have to connect a RC. Here R value I have to increase it. Here, see over here, the output voltage is somehow or the other getting distracted, getting flattened out. The current is reducing, the input current is reducing, and the voltage is somehow increasing. This is the RC, effect of RC. Diode current and same the diode current as well as the diode voltage. Right? Similarly, you can go for a RL load also. L value you have to significantly increase. CD. Yeah. Here you can see the value of, as the value of L is increasing, your output voltage is getting a negative cycle, getting a signal in the negative portion, right? This is due to the inductance. This is due to the inductance. As you can see, I have talked about the switch. Here diode acts as a switch. Previously, it was acting as a unipolar switch, only one polarity of the voltage. Till now, what you have seen was only the positive part of the voltage was shown, but now, due to the value of L, it is acting as a bipolar switch. It is acting as a bipolar switch. As the value of L is increasing, there is a negative, see over here, there is a negative aspect over here, right? The output voltage getting negative. This is higher value of L, right? So here the diode acts as a bipolar switch. Previous cases it was acting as a unipolar switch, right? Any doubt regarding this? This is the up half-wave rectifiers with all different loads, R, RL, RC, C, all those things. You saw the source voltage, source current, load voltage, load current, as well as diode voltage, as well as diode current. See over here, the diode current is also getting, the diode voltage is also getting negative. That means we are having a bipolar switch. Diode is acting as a bipolar switch. Similarly, bridge rectifiers similarly full wave rectifiers can also be done. In full wave rectifiers, you have to find, you use a transformer. Half wave rectifiers are not efficient because of the only one half cycle is represented because of the diode, single diode. But due to full wave rectifiers, in the full wave rectifiers, both the half of the cycle is getting, so that it is much more efficient. It's twice the efficiency of the half wave rectifier. Similarly, you can do the full wave rectifiers also in Simulink. And how to negate this particular negative aspect? Any idea, anyone? Negative response, how we should overcome it? It is with the help of a freewheeling diode. It is with the help of a freewheeling diode. Here I will use a freewheeling diode, same diode only, but it's much faster. When I run it, you can see the negative axis in the output has been curtailed. The negative portion of the output, rectifier output, has been curtailed because of the freewheeling diode. Because of the freewheeling diode. And here also you can see the diode voltage, diode current. See the same diode voltage as well as diode current. Any doubt regarding this? Okay. So this is the freewheeling diode. D is the diode and FD is the freewheeling diode. Measurement and the calculation is shown over here. V0 equal to Vm by pi. I0 equal to Vm by pi R. Similarly, you can do for RE load as well as RLE load. All this diagram I have provided. Similarly, you can go for a full wave rectifier. See the calculation for the full wave rectifier. In a full wave rectifier, you have multiple number of diodes and a transformer. You have multiple number of diodes and a transformer. Because of the inclusion of multiple number of diodes, the positive half cycle as well as the negative half cycle of the output voltage comes, which increases the efficiency of the full wave rectifier. There are two different type of full wave rectifier. One is a midpoint full wave rectifier, and second one is a bridge type full wave rectifier. Bridge type is widely used because for midpoint you need a center type transformer. A center type transformer is nothing but where there is a tapping in the secondary axis of the transformer. Here we have, whenever we are using a transformer, there is a term that comes in use that is called as a transformer utility factor, TUF. Because all of you might be well aware of what a ripple factor, what a form factor in the perspective of rectifiers. But whenever we are using a transformer, another term gets added up that is called as a transformer utility factor. Transformer utility factor is the ratio between the DC power to the RMS voltage and RMS current. That is, numerically speaking, PDC divided by VRMS into IRMS. All of you can calculate, provided the voltage and current value, all of you can calculate what is PRMS, IRMS, PDC, and you can easily find out what is the transformer utility factor. This is only valid for a transformer only, for a rectifier utilizing transformer. As you can see, it's a midpoint transformer, midpoint full wave midpoint AC/DC rectifier. This is the source voltage, this is the output voltage, this is the output current, whereas the output voltage and output current have twice the system, both positive as well as the negative half cycle. Any doubt over here? So clear it out. Bridge type, yesterday we have seen what the bridge type, and we see the comparative analysis between the half wave, full wave, and full wave center tap as well as full wave bridge. Initially in half wave, the average output voltage is Vm by pi, whereas in full wave it is 2 Vm by pi, and in bridge it is 2 Vm by pi. RMS is Vm by 2, whereas in full wave it is Vm by root 2. Ripple voltage is 0.3856 Vm, around 0.3077 Vm. Voltage ripple factor is 1.2, which is pretty high, but in full wave and full wave center tap and full wave bridge it is around 48%, whereas in half wave it is 121%. The rectification efficiency is for half wave it is 40.53%, whereas in full wave it is 81.06. That's exactly the double of the half wave. Whereas the transformer utilization factor in half wave is pretty low, whereas in full wave bridge it is pretty high. Peak inverse voltage for diode, especially, that is 2 Vm and Vm in full wave. Thrust factor is 1.141. Number of diodes are increasing, and the ripple frequency also increases. Here in a control rectifier also I have given the table of different values. This is all will be known if you have read it in Power Electronics from PS Bimra and all. It will be useful for you to get a revision over here so that it also comes in different competitive examinations. If you remember these formulas, you can directly solve these questions. Okay. So this completes the basic rectifier. Then with a single phase source. We can also go for a three-phase source. Three-phase half wave as well as three-phase full wave. The calculations are much more lengthier and complicated because of the inclusion of two more phases like RYB, so it will be much complicated. But there are advantages of what is the basic advantages of three phase. Basically, for output power higher than 15 kilowatt, we use polyphase circuit. If you require a output power which is higher than 15 kilowatt, you need a polyphase circuit. In a polyphase circuit, you have a better transformer utilization factor, better input power factor, lesser ripple content in the output current, and also because of higher transformer utilization factor, your size of the filter components will be lower. These all are the advantages of a polyphase rectifier circuit. Many times it is called as a pulse circuit also. It is termed as a 6 pulse, 12 pulse, 24 pulse, 48 pulse, 64 pulse, up to 64 pulse it is possible. So pulse means the number of switches basically. In single phase, you can have maximum 4 switches. But in three phase, the minimum number of switches is 6. Minimum number of switches is 6. If you are using a three-phase three-wire configuration. If you are using a three-phase 4-wire configuration, the minimum number of switches are 8. So as the number of switches increases, the complexity of the circuit also increases exponentially. But on the safer side, on the brighter side of the view, what we can do is that we can have a higher conversion efficiency, higher transformer utilization, lesser ripple, and the sizes of physical sizes of the components, like components in these terms of inductors and capacitors, will be much lower. And the input power factors are also quite a bit interesting here. Input power factor will be also better than the half wave on single phase one. As you know, there are three different phases R, Y, B, both separated by 120-degree phase shift. So the average output voltage V0 equal to 3 pi integration of pi by 6 to pi by 2 VML sine omega t plus 30. That whenever you compute it, you will find 306 Vp divided by pi. And similarly, RMS voltage will be total square root of the average voltage with the change in the definite integration, that is pi by 3 to 2 pi by 3, and that you will get 0.955 PML, and the ripple voltage is 0.0408 PML, which is far lesser than single phase circuit, and voltage ripple factor will be 4% only, whereas you have seen in a half wave that was around 40%. Sorry, around 121%, right? Which is now, as the number of switches increases, the ripple factor drastically decreases. Form factor, RMS value, all these calculations are available in the books. This is for the review purposes. And the transformer utilization factor is much higher than the full wave circuit. It was around at 0.81, now it is 0.95 transformer utilization factor. And the efficiency here is 95%. Efficiency over here is 95%, which is much better, right? Okay, we will discuss it in the next class, Monday. Today we discuss about what is a single phase circuit, single phase rectifier, what are the switches, different classification of switches, and single phase rectifier, half wave as well as full wave, and studied the different mathematical aspects of this thing. If any doubt, do ask.